Hi, everyone. Welcome. Please take your seats. We're about to get started. So if everyone could please take a seat, we're going to get started momentarily.
Hello, everyone, and thank you so much for coming. My name is Daria Dyaneem, and I'm the Prize Lecture Chair of Yale Society of Physics Students. We are delighted to have Professor Kip Thorne joining us as our Howard L. Schultz Senior Lecturer this afternoon. Howard L. Schultz Sr. was one of the longest tenured professors in the history of the Yale Physics Department, serving for 32 years. In 2018, SPS decided to celebrate the legacy of Professor Schultz by establishing a lecture series in his name. Each fall, we invite a distinguished physicist to speak about their life and work and engage with students on campus. For undergraduates especially, this opportunity can mean a tremendous amount. Our speakers are groundbreaking truth seekers who serve as incredible examples, role models, and inspirations. Today, we are joined by a scientist who is an embodiment of these qualities, Kip Thorne, Professor Emeritus of Physics at Caltech. From 1967 to 2009, Kip led a research group working in relativistic astrophysics and gravitational physics, with an emphasis on relativistic stars, black holes, and especially gravitational waves. 53 students received their PhDs under his mentorship, and he mentored roughly 60 postdoctoral students. He has co-authored several important textbooks and was sole author of Black Holes and Time Warps, Einstein's Outrageous Legacy. Along with Rainer Weiss and Ronald Drever, Kip co-founded the Laser Interferometer Gravitational Wave Observatory Project, LIGO. In the hands of a younger generation of physicists, LIGO made the breakthrough discovery of gravitational waves arriving at Earth from the distant universe on September 14, 2015. For his contributions to LIGO and to gravitational wave research, Kip shared the Nobel Prize in 2017 in physics, among many other awards. In 2019, Kip stepped down from Caltech's professorship to ramp up a new career at the interface between art and science. This new career has included, among other things, a recent book, The Warped Side of Our Universe, consisting of Kip's poetry, tightly integrated with paintings by Leah Halloran, and of course, Christopher Nolan's 2014 movie Interstellar, which sprang from a treatment Kip co-authored and for which he was executive producer and science advisor. In Kip's book, The Science of Interstellar, Kip is currently working with colleagues on a detailed history of LIGO. Can all the undergrads in the room please stand up? Look how many there are of you. You guys can sit back down. My job as lecture chair was to bring a lecture that undergrads would be excited about, as we have seen has been succeeded. As I asked around about who to bring, a fellow student recommended Kip. My first thought was that it was too ambitious, but as we can see, I was wrong. I wanted to quickly express my deepest gratitude to Professor Mingarelli for helping us reach out to Professor Thorne in making this dream a reality. And finally, please put your hands together to warmly welcome Professor Kip Thorne.
Thank you very much, Daria. And I do prefer to be called Kip, and I asked her to do that in the introduction. She slipped at the very end and used the wrong name, but thank you. So, in 1962, I went to Princeton University from Caltech, where I'd been an undergraduate, to study under John Archibald Wheeler. He was the great guru of relativity theory in that era. And I knew that that was the area I wanted to do a PhD thesis in. And from Professor Wheeler, or Johnny as I learned to call him later, I learned that there might be in our universe what today I call the warped side to our universe, though that's not the phrase we used at the time. By this I mean objects and phenomena that are made from warped space and time, including black holes, gravitational waves, the Big Bang, birth of the universe, vacuum fluctuations, which you may be surprised to see there, but I will explain why they're there and why you can't avoid having them there. Excuse me. And then the wormholes. Now, the great richness of the warp side of the side phenomena is illustrated by black holes. So I'm going to talk for a little while about black holes alone, just to give you some sense of this great richness. This is from the movie Interstellar. It is Interstellar's black hole Gargantua. And you might be surprised, people were surprised when they first saw this in the movie, that it looks like this. And the question was why? And the answer is that because the black hole is surrounded by an accretion disk, very hot gas, that is orbiting around the disk, much like Saturn's rings, and gradually spiraling in and finally falling, orbiting around the black hole, and gradually spiraling in and ultimately falling into the black hole. And the light rays from the upper back face of the disk go up over the black hole, and pulled by the hole's enormous gravity, they come down to the camera, an IMAX camera in this case. Christopher Nolan always films his movies in IMAX. And it comes down to the camera like that. And so, of course, it produces this upper branch of the image. And similarly, a light ray from the bottom back face goes under the black hole enough and produces the bottom part of the image. And then a light ray from the front of the disk, the camera is just above the plane of the disk. It goes to the camera and produces this crossbar. So a very simple explanation. Now, back in just a few years ago, the Event Horizon Telescope, in 2019, it observed a black hole in the M87 galaxy. This was its first big, exciting observation. This is a collaboration of about 400 scientists and engineers at 100 institutions led by Shep Doleman at Harvard. And it combined the data from many radio telescopes worldwide operating at 1.3 millimeter wavelength. These are a few of the telescopes. These are the locations of those telescopes. Combined those coherently to produce an image. And this is the image that they got. And from the image, knowing how far away the galaxy is in which M87, in which this black hole resides, it was possible to deduce that the mass of the black hole is about 6 billion times the mass of the sun. Now, compare this with the image you saw in Gargantua, the movie image in Interstellar. Many people have commented on how similar they are. I would prefer to say how very, very different they are. And so the question is, why are they so different? And so let's take the black hole in Interstellar, and let's move the camera from the equatorial plane up to the North Pole, and then fuzz it out because the Event Horizon Telescope does not have very good resolution. And then it looks like that, except it's lopsided. Aside from being lopsided, it looks basically the same as what the one in Interstellar would look like. It's lopsided because there is a Doppler shift. The gas going around the black hole is moving toward you on this side and away on that side, and so it's much brighter on this side than on the left-hand side. And I discussed this with Christopher Nolan, and we became very good friends. We need to make it lopsided. He said, no, it's not lopsided. I said, of course it's lopsided. He said, no, the human eye is incapable of distinguishing brightness or color when an image is this bright. And so we want this to be the way that the human eye would see it. And the human eye would simply not be able to distinguish this Doppler shift. So although the camera would, and although astronomers always show it, not in my movie, Chris says. And so you got what you got. Now, black holes are made from warped space-time, and by this I mean, or I'm saying something that is summarized by saying that the circumference of this black hole is much smaller than its diameter. And you might ask, well, how is that possible? And the answer is, let's do an analogy. Let's take a child's trampoline, a sheet of rubber, put it up on high stilts, and then put a rock at the center, and it bends the rubber down like that. and then pretend you're an ant. You're a blind ant, but you have a physics degree from Yale. And so you are real smart, and so you go marching around and you measure the circumference, and then you go measure the diameter, and the diameter is enormous compared to the circumference you find as you march around. And you say, obviously, I live in a warped space-time. Space-time is warped around us. So this same kind of diagram, identically the same diagram, can explain what goes on in the case of a black hole. All you do is change the images. Now, what we're looking at is a two-dimensional slice through the equator of that black hole. And we're looking at that two-dimensional slice, now a two-dimensional surface, embedded in a higher dimensional space, which a physicist might call, or mathematician might call the embedding space. You've embedded this two-dimensional surface in a higher dimensional flat space in order to be able to visualize the warping of this space. And so that higher dimensional flat space is called the bulk by physicists sometimes. It's called the fifth dimension in the movie Interstellar, because the fourth dimension is time. And the rock down at the bottom is replaced by a singularity that I will return to as well. But just remember then, as seen from the bulk, the black hole looks like a funnel. And I'll refer back to this funnel. Now, what we all know about particularly is that if I fall into that black hole trying to send signals to you with a microwave antenna, once I fall through the surface of the black hole, called its horizon, the signals I'm trying to send to you and I get pulled downward, and neither the signals nor I can ever get back out. And we're pulled down into this singularity down here at the center. And so that's another remarkable aspect of the black hole, is the horizon and the downward falling inside the singularity. Now, you also have a warping of time in addition to the warping of space around a black hole. Time slows as you near the horizon. So in the case of the movie Interstellar, Miller's planet in the movie, the water planet, is quite close to the horizon, and 1 hour on Miller's planet is 7 years on Earth, which we can discuss. And the comments by people in the New York Times and elsewhere when the movie first came out was, that's impossible, but they hadn't done the real calculation. For the Kerr metric for a spinning black hole, it's possible, but not very plausible that it spins that fast, but it's possible. So time slows then to a halt at the horizon, as seen by an observer who is hovering above the horizon compared to far away. And inside the horizon, time flows in a direction you would have thought was a space direction toward the singularity. And that's why nothing can get out of the black hole, signals or I, because we would have to move backward against the local flow of time, and that's impossible. Now, backward time travel might be possible, but not locally. You have to go out in space and come back before you started, but you can't go against the local flow of time. And so this down cascading time is a phrase I like to use. It goes on inside the horizon. Finally, the black hole spins, and it creates it drags inertial frames, is the technical phrase. It creates a whirl of space around the black hole like the air in a tornado, fast angular velocity near the horizon, much slower farther away. So that was just my hand sketch. This is the actual geometry of space-time as seen from the bulk, from the higher dimension, for a fast-spinning black hole. This is the shape that you have. The horizon is down here. It looks like a circle, but that's because I've removed one space dimension, remember. That when I put that one space dimension back in, I have a flattened sphere, it turns out. The color coding is the slowing of time, the rate of flow of time compared to the rate of flow of time back up at very high altitude. Where it's yellow, time is flowing at 10% the rate that it is far away. And then the white arrows indicate the angular velocity of dragging of space into motion, or dragging of inertial frames, as they say. Now, what warps the black hole space and time? The answer is the energy contained in the warping. The black hole is held together by nonlinear self-interaction. It's what we might call a gravitational soliton in that sense. Now, so my collaborator, Leah Halloran, on this book that we wrote about the warp side of our universe, has made some paintings that I'm going to use in my talk. This is one of hers. If I take my wife, this is in the book, it's actually Leah's wife, and she's suspended just above the horizon or falling in. Her feet are dragged around faster than her head because of this frame dragging. The dragging of inertial frames is greater near the horizon than it is farther away. So her head see her feet going counterclockwise around. This is, if you had gyroscopes on her feet and gyroscopes on her head, the gyroscope at her feet would be precessing counterclockwise as seen by her head. Similarly, the gyroscope at her head will be precessing counterclockwise. It's like taking a wet towel and wringing water out of the wet towel. If your left hand sees your right hand going counterclockwise, then your right hand sees the left hand going counterclockwise. So there's a counterclockwise vortex of twisting space at the north pole of the black hole, a clockwise vortex of twisting space at the south pole of the north pole of the black hole. There's also tidal gravity that is quite familiar to you. It's the same thing that races the tides on the Earth's oceans, as seen from the usual viewpoint. The gravitational pull of the moon is stronger on the near side than on the far side. And so the Earth's oceans get pulled up toward the moon faster than the center of the Earth, and those at the far side get pulled up less with a smaller acceleration than the center of the Earth. So seen by the Earth in its basically freely falling reference frame, all that amounts to is a squeeze transversely, because these arrows are inward toward the moon, a squeeze transversely and a stretching horizontally, vertically. This is, I think, all very familiar to you. But there's an alternative point of view that you can take, and that is that there's something called a tendex. Tendex comes from the Italian, or from the Latin, for to stretch, just as vortex comes from the Latin for to turn. And so there's a tendex sticking out of the black hole that stretches my wife or Leah's wife or me, if you're near the Earth, and squeezes in that direction. So that's why it's painted blue. And so there's squeezing in this direction, stretching in this direction by these tendencies that stretch and squeeze. Now, similarly with the case of a black hole, it's a planet, Miller's planet in the movie Interstellar, is stretched and squeezed by tendencies that are produced by the black hole. And so this is part of the backstory in the movie Interstellar. Now, people who are experts in relativity in this audience, few of you have probably even heard about tendencies and vortices. And so if you want to know what underpins this, you'll find the details of this, the mathematics of these tendencies and vortices, in my textbook with Roger Blanford, either in the great big volume, Modern Classical Physics, or in the single volume, Relativity and Cosmology, in these particular boxes inside there. But let me just tell you in words for the experts. If you take the Riemann curvature tensor, which is the thing we always think of as producing a stretching and a squeezing, and you look in a particular reference frame, you have to do that. And I want the vacuum Riemann tensor, so there's no matter around for simplicity. Then it breaks up, you look at the irreducible tensorial parts, using the language of group theory. Irreducible tensorial parts of the Riemann tensor. They are two symmetric trace-free tensors. One is the tidal field that stretches and squeezes. And the other is the frame drag field that represents this differential precession. And that's what underlies this. And there's a detailed mathematics and a detailed way to take that and visualize it in terms of vortex lines and tendex lines, which you can read about in there. But it's something that students of Yanbei Chen, after I retired, I worked with Yanbei Chen and his students. He was one of my successors at Caltech. And they worked this out by looking at movies, numerical relativity generated movies, and then doing analytical calculations to figure out what was going on. Okay, so let's talk about the interior of the black hole. In the movie Interstellar, Cooper plunges through the gargantuous horizon into the interior, and you watch and listen as he says, "I'm crossing the horizon." Now, let's look up here. So up here above him, you see the black hole. He's going into the black hole, and the external universe is out there to the right. Okay? Now, let's watch what happens after he goes inside the horizon. Now you notice the external universe is on this side, but the ring is now surrounding the external universe. It was surrounding the black hole. It's now surrounding the external universe as he looks back up from inside the black hole. That's what really happens. The Interstellar, in almost all respects, is a precise computer-generated visualization of what would happen. And I just find this quite interesting, quite remarkable. Of course, light can fall into the black hole, and you can see out of the black hole, but you can't see into the black hole. From inside you can see out, but from outside you can't see in. Okay, let's keep going. So in the movie Interstellar, Cooper in the Ranger spacecraft, goes through the horizon, down, and below him there is what is called a chaotic singularity. For physicists, it's also the BKL singularity. It's a region where the laws of physics fail because the space-time curvature becomes so large and the laws of quantum gravity presumably take over. But as the best we understand it, there are two other singularities inside a black hole. There are three different kinds of singularities. There's what I prefer to call an infalling singularity, though this is technically among the physicists is called the mass inflation singularity. But what this is caused by is that time is so slowed down inside here that as Cooper falls into the black hole, everything that will fall into the black hole in the future history of the universe, the next billions and billions of years, comes crashing down as seen by him on top of him in a fraction of a second, in a sort of a shock wave. And this is the so-called mass inflation singularity or infalling singularity. And everything that of all the stuff that fell into the black hole in the past, which could be hundreds or thousands or millions of years, some of it gets scattered back upward in a weaker outflying singularity, or also sometimes physicists often call it the chaotic singularity. So you've got three singularities inside a black hole. And this is all in Interstellar, but it's not in most textbooks, only the most recent textbooks. So you have to go into Interstellar to learn your relativity. Okay. But in the movie, Cooper is rescued by the tesseract, which is a cube in 4 dimensions called a tesseract. If you look in the movie very carefully, you see the Ranger torn apart by tidal forces, just very briefly. And Cooper is out in free fall and falls into this tesseract. And then the tesseract carries him out of the black hole into the 5th dimension, up into the bulk and back to Earth. Now, the climax and the ending of Interstellar is something that Christopher Nolan and I worked out very carefully with long discussions. And the only place you'll read about what the real backstory is in my book. Chapters 27 to 31. I'm not going to tell you, but if you haven't read my book, The Science of Interstellar, it's on sale in your local bookstore. Okay. But the other book that is very near and dear to my heart is my book with Leah Halloran, The Warped Side of Our Universe, a more recent book, An Odyssey Through Black Holes, Wormholes, Time Travel, and Gravitational Waves. And here you see a black hole, a painting of hers. You see the funnel that in the higher dimension, in the bulk, and you see her wife falling into the black hole, Felicia falling into the black hole. And I'm now going to answer the question, what is a black hole, by playing a film clip that is based on the movie. And so you hear my poetry, my attempts at poetry, and you see her paintings explaining what's inside, what a black hole is. Okay. And that's why I spent the first pretty big piece of this lecture on black holes, to give you some sense that there really is an enormous richness to the warp side of our universe. You have this black hole that has all these different features, all of them made from warped space-time, matter not involved in them whatsoever. And that really is the essence of the black hole, is all of these different features. Animation was by Paula Froley, based on Leah's paintings. So let me talk about gravitational waves now for a few minutes. Albert Einstein predicted gravitational waves in 1916, and we can understand a gravitational wave by imagining a number of particles out in space floating freely in a square array. A gravitational wave is going to go into the screen, and as it goes into the screen, it stretches and squeezes space. It has Tendex lines that stretch horizontally and Tendex lines that squeeze vertically, and then that stretch and squeeze are oscillatory, as seen like that. Another way to say it is that local inertial frame here and there do not mesh together. Instead, the local inertial frames move back and forth, respect each other, and any particle that's at rest in a local inertial frame, those particles, they move back and forth, marking out what you might say is the stretching and squeezing of space, the stretching and squeezing of local inertial frames relative to each other. The word Tendex then is a collection of Tendex lines, and I've shown you Tendex lines. And again, there's mathematics under Tendex lines, and then Tendex that you can see in this textbook I referred you to. Okay. Now, there are only two types of waves, as far as we can tell, that exist in the universe for exploring the universe, that can be created far away and travel to Earth and tell us about what's going on far away. Electromagnetic waves, light, radio waves, X-rays, and gamma rays, and gravitational waves. And it was Galileo 400 years ago who built a little optical telescope, pointed at Jupiter, discovered Jupiter's four largest moons, and in the process initiated instrument-based electromagnetic astronomy. And so in 1972, I and colleagues began to work toward a vision of doing what Galileo did, creating gravitational wave astronomy, just as Galileo had created this instrument-based electromagnetic astronomy. In that same year, 1972, Ray Weiss sent to me and other colleagues from MIT a technical paper that he had not published in the regular literature, but had just put into a quarterly progress report, an internal MIT series, in which he proposed the idea of a gravitational wave interferometer of the sort that we would ultimately build for LIGO. And he analyzed all the major noise sources that he could identify that this would face, and did detailed calculations of how large those would be and how you might try to deal with them and drive them down to a low level, and how low you might be able to drive them, and therefore what kind of sensitivity you might be able to achieve. And let me make the further mark that gravitational waves are made from the same thing as black holes, warped space-time, so they're the ideal tool for exploring the warp side of our universe. Now, I was initially very skeptical about Ray's idea, and I came around only after about 3 years of studying it, talking with him, talking with other experimental colleagues. And then we ultimately then formed a collaboration between Caltech and MIT to do this. And after 43 years of intense work to develop and perfect Ray Weiss's interferometers, as elaborated by Ron Drever, who invented a number of things that were improvements on Ray's original idea, and others. And after the work of a 1,000-person LIGO team, organized and assembled and initially led by Barry Barish, they designed and built advanced gravity wave interferometers and developed data analysis techniques. And after 60 years to develop tools for simulating on computers the collisions of black holes by solving Einstein's equations numerically, numerical relativity. So I have summarized here in about 1 minute an enormous amount of work by thousands of people in different areas working on this. Finally, on September 14 of 2015, the first gravitational wave signal came into LIGO, our Laser Interferometer Gravitational Wave Observatory, from colliding black holes. And this is a simulation by the SXS Numerical Relativity Collaboration. It's a collaboration between Caltech and Cornell. It's led by Saul Tucholsky, who was originally at Cornell. He's now at Caltech, but he has led this collaboration from the very beginning. And what you're going to see is what this black hole merger looks like as seen from the bulk. So you see the two funnels here. These are the two black holes as seen from the higher dimension. You see a color coding, which is the slowing of time as you near the horizon. And you see arrows, which is basically the dragging of space into motion. But these black holes are not spinning in this particular case, so you don't see the whirling around the black holes. And let's let this roll. The movie is slowed down into slow motion, so you can see the enormous splash in the shape of space as seen from the bulk, and the then oscillations in the shape of space and the oscillations of the rate of flow of time. And that storm, as I like to call it, in the shape of space and time is what produced the gravitational waves that go traveling outward. But this movie only captures a small fraction of what goes on the warped side of the universe in this black hole collision. And so it was this collaboration that I wound up doing with Yanbei Chen's students and postdocs, in which we then developed the concepts of vortices and tendencies and discovered that when the black holes collide, and this is as seen in our universe, sticking out of the ends of this dumbbell-like thing, there are stretching tendencies in blue, squeezing tendencies in red, and as the two black holes orbit around each other and are merging, these tendencies stretch back like that, like water from a whirling sprinkler head. And similarly, from the merger region, so there's a squeezing tendencies coming out, and these stretching tendencies around, and those also swing back and out as the black holes go around each other. And these become the gravitational waves when they reach Earth. It's quite remarkable. This is what's going on. We didn't know this was what was going on until we had computer simulations and saw it in the simulations and then understood things analytically. But that's only half of the gravitational waves. There's a second set of gravitational waves. The first set was generated by tendencies that stick out of the black hole to do the stretching and squeezing. Here it's vortices of twisting space sticking out of the black hole. And so you have a counterclockwise vortex and a clockwise vortex sticking out of the north and south poles of this black hole. Here we're seeing this from the bulk, looking in from the bulk. And then we have over that black hole has the clockwise vortices and the counterclockwise vortices. This is basically a head-on, or this is a black hole collision in which the vortices and tendencies on the two holes are pointing in opposite directions. Okay, so where are the gravitational waves? Well, now this is the rather remarkable thing, is that outflying vortices generate entwined tendencies that stretch and squeeze. And so here's Leah's painting. As these vortices move outward toward Earth, their motion generates tendencies that wrap around. And similarly for each of these. And the mathematics underlying that is rather pretty. It's the Bianchi identities of general relativity, for those of you who know about general relativity and Bianchi identities, which written in terms of the tidal field and the frame drag field, they look just like the dynamical Maxwell equations. But here it's a time derivative of a symmetric trace-free tensor, curl of this symmetric trace-free tensor, and then symmetrized. But otherwise, it looks just like Maxwell's equations. And just as Maxwell's equations say that if you begin by a magnetic field and you move it, you generate an electric field. So these Bianchi identities say that if you begin with a tidal field, vortices and tendencies, and if you begin with a frame drag field, which is described by vortices, and you move those vortices, they generate tendencies. They generate the tidal field. So it's really a very, very beautiful piece of mathematics that, again, people didn't appreciate. We didn't really appreciate it until we saw it in computer simulations and then started thinking this through. Okay, those gravitational waves were emitted in a galaxy. I'm sorry if I hit somebody's eyes. I shouldn't do that. I've got enough. I'm being a bad boy, excuse me. So the gravitational waves were generated in a galaxy far away, 1 billion light years from Earth. They traveled out into the universe and across the universe, and they arrived at the outer reaches of our Milky Way galaxy 50,000 years ago, when the Earth, we humans, our ancestors shared the Earth with the Neanderthals. And they traveled through the galaxy to Earth, arrived near the South Pole of the Earth on 14 September of 2015. They traveled up through the Earth and emerged at the Livingston, Louisiana site of LIGO, the Laser Interferometer Gravitational Wave Observatory, which was sitting there waiting for them to come. And 7 milliseconds later, they came up through the Earth at Hanford, Washington, our other LIGO site. The LIGO team, together with the Virgo team in Europe, which had built their own gravity wave interferometer, but were not yet fully operational. We analyzed the data jointly among a team of 1,000 authors on this paper, and the result was announced then the following February. And the signal, by comparing with the numerical relativity waveforms from the SXS simulation, of which I showed you the movie, with the cleaned up signal, we found that, or the LIGO and Virgo teams found that this was an initial black holes, 29 and 36 solar masses for a total of 65 solar masses, final black hole of 62 solar masses, 3 solar masses going into gravitational waves. Imagine destroying 3 suns, turning all of that into gravitational waves. The total power output during the merger, which is a matter of something like a few hundredths of a second during the merger, the total power output was 50 times larger than the total luminosity electromagnetically of all the stars in the universe put together. It's really quite remarkable. No electromagnetic waves found whatsoever coming from a distance of 1.3 billion light years. LIGO has now seen about 300 black hole collisions, and it has used those to explore the laws of black hole mechanics, the properties and populations of black holes in our universe. It has seen several collisions of neutron stars, only one of which we've seen the electromagnetic waves from. The others are too far away. several black holes swallowing neutron stars, also too far away to see the electromagnetic waves as yet. And so LIGO is exploring the warp side of our universe with gravitational waves, which was our goal. The holy grail of this is to explore the Big Bang birth of our universe with gravitational waves, and that's what I find really exciting, looking off toward the future. And so let me move toward that as I move into the topic of vacuum fluctuations in the warp side of our universe. I first learned about vacuum fluctuations and their possible importance astrophysically from Yakov Borisovich Zeldovich. He was together with Andrei Sakharov. They were the fathers of the Russian hydrogen bomb. And like John Wheeler, my mentor, when they left nuclear weapons research, they moved into astrophysics. And Zeldovich actually became one of my principal mentors. I learned a lot from John Wheeler, but I learned almost as much from Zeldovich. And I was commuting back and forth to Moscow roughly once a year and spending times of typically a month a year during that entire period from about 1968 until the Soviet Union crumbled in 1991. So it was Zeldovich who called our attention to the importance of vacuum fluctuations. So what are they? If you take a box and you remove everything that possibly can be removed from the box, then you're left with tiny fluctuations that are required by Heisenberg's uncertainty principle, required by the laws of quantum mechanics, in which fluctuations of everything that could have resided inside the box. So electromagnetic fluctuations, which means photons fluctuating in and out of existence, virtual photons we sometimes call them. Similarly, virtual electrons and positrons fluctuating in and out of existence, or just think of them as classical fields, if you wish, that are fluctuating, that have very, very tiny amounts of energy. This is Leah Halloran's painting of this, basically the probability densities for having electromagnetic waves, a high probability in here, a low probability there, in the vacant regions in here, very low probability, these probabilities are fluctuating. So you can think about this in a variety of ways like that. These fluctuations have essentially no energy and produce no gravity. Now, it's quite possible that they are responsible for the tiny residual cosmological constant that you see, or to put it differently, for the acceleration of the universe. But that the amount of energy, if after you have renormalized in quantum field theory, renormalize the energy of the vacuum, if it doesn't renormalize to precisely zero, it renormalizes to a level that is so small that it's irrelevant for my talk today. So I'm going to set that aside, set aside the issue of the cosmological constant, or the acceleration of the universe. Now, in 1973, I took Stephen Hawking to Moscow. My Russian colleagues wanted to meet him. He wanted to go. So I took him, and we met with Zeldovich and one of his students in a Hotel Rossiya in Moscow. The student was Alexei Starobinsky, and it was Zeldovich, Starobinsky, and me in this conversation. And Zeldovich asserted, and then Starobinsky sketched a proof. So Zeldovich doing this on the basis of his physical intuition, then Starobinsky, who was very deep in relativity and in quantum theory, sketched a proof that vacuum fluctuations bathing a spinning black hole, so coming in, and Leah's here painting this only coming from one side, they're really coming from all sides. But just to visualize this, she's painting them going from one side. That those vacuum fluctuations suck up energy from the black hole spin to convert into real radiation flying away. So if you don't know about the vacuum fluctuations, it just looks like this spinning black hole is radiating photons and particles, photons, electrons, protons, positrons, all kinds of fundamental particles as well, it's spontaneously creating particles and emitting them, but it's really an amplification of the vacuum fluctuations. Now, in December, Stephen went home to Cambridge, and he thought about this, and in December 1973, he had an epiphany. He said, let's think about a star that is imploding, a spherical star, not spinning. It implodes to form a black hole, and the black hole grows. And as it grows from the interior of the star outward. And locally, the horizon of the black hole is basically moving outward at the speed of light relative to local inertial frames. And it grows and grows and grows and grows until the black hole swallows the star. Let's talk about that situation. And so he did a calculation in which he showed then that vacuum fluctuations falling onto the black hole, again we show them only coming from the left, but they're really going from all directions. Coming onto the black hole, they interact with the expanding space near the black hole to get energy out of it. They basically swallow energy from the expansion of space at the horizon as the horizon is growing, and turn themselves into real outflying radiation, which is Hawking radiation, the very famous Hawking radiation. And that was an enormous surprise to people, and it was really triggered, as I say, by Zeldovich and the whole issue of vacuum fluctuations. Now, Zeldovich at that same time, the same period, 1971, he began to ask what role might vacuum fluctuations have played in the birth of their universe. And he did calculations. You find these calculations there's a book on cosmology that Zeldovich and Novikov wrote, and the English translation was in the early to mid-70s. And in that cosmology, you find his calculations. He just can't make this produce anything really interesting. And so he's rather puzzled. He thinks that the universe being born in a Big Bang singularity, it ought to produce something like Hawking radiation, but he's not getting anything very interesting out. However, his student Alexei Starobinsky and Andrei Linde, who was also in Moscow at the time, and then Alan Guth at Harvard, they had a brilliant idea that if the universe had this early era of inflationary expansion, then it might be quite different. Indeed, they found in their calculations that the Big Bang singularity, if it produced only vacuum fluctuations, which fed off the energy of inflationary space expansion, they would produce all the matter and radiation in our universe and would produce that with inhomogeneities, or just the right kinds of inhomogeneities to explain the births of the clusters of galaxies, the structure we see in our universe. Just a remarkable discovery. And so again, you see vacuum fluctuations playing this really amazing role here in the possible role in the birth of our universe. Let me just make a side remark here. I think that the search for primordial gravitational waves as being produced by this process is a very important thing. They may be seen through their influence on the polarization of the cosmic microwave background. Those of you who know about this, so-called B modes, and getting a clean observation of primordial B modes in the cosmic microwave background is a real holy grail of the people who work on the cosmic microwave background, because they would tell us then a lot about the birth of the universe, about inflation. And in the middle of this century sometime, we may have a successor to the LISA gravity wave mission called the Big Bang Observer, and the particular feasibility study that Sturl Finney led a few years ago. And that would have a real shot at seeing the primordial gravitational waves produced in this manner at periods of a few seconds. So we have the prospect to see the gravitational waves from something like this. And I have the hope and the expectation that what we see will not be compatible with this beautiful idea of vacuum fluctuations. I've had this discussion with students here today. And that will be so exciting if that happens, because that then is a key to understanding what we've got wrong in our current theories of quantum gravity and the birth of the universe. And so anyway, that's one of my dreams for the future. Let me just say a few words about wormholes quite quickly. Albert Einstein and Nathan Rosen in 1965, they conceived the idea of a wormhole. And of course, there's a wormhole in the movie Interstellar. And this wormhole is a bridge that goes from the vicinity of the distant galaxy where the black hole Gargantua lives to the vicinity of Saturn. And the IMAX camera looks through this to see what the light coming in, producing an image coming in through the wormhole up to the IMAX camera looks like. And this is the image you see in the movie Interstellar. The problem with wormholes, however, as John Wheeler discovered in 1962, is that they tend to pinch off so fast that nothing can travel through unless you do something to hold them open. And so holding a wormhole open became a real challenge. And as best I can see, the only hope to hold a wormhole open is to put a material inside the wormhole that repels gravitationally. I like to call this exotic matter. And the only way I know to make exotic matter is by manipulating vacuum fluctuations. By manipulating vacuum fluctuations, you can make stuff where there's lower vacuum fluctuations than the normal vacuum has, which repels gravitationally. Now, what is the bottom line? And this is a whole area of research that went on from the, I guess it was the late 80s up until now. Bottom line, can wormholes occur naturally? I think the bottom line is almost certainly no, except perhaps in quantum foam that exists on the Planck scale. So these are vacuum fluctuations. These are fluctuations of topology of space on this very, very tiny quantum gravity scale. Can they be made by an advanced civilization? Possibly. You could imagine a very advanced civilization grabbing some of these wormholes out of the quantum foam and enlarging them to classical size. That's the kind of thing I would normally only discuss over a few vodkas. Beer wouldn't be enough. So I throw it out, but I mean, this is much more speculative than anything in Interstellar. Can they be held open? The bottom line of a number of long calculations that people have done is probably not. It probably requires too large amounts of exotic matter. However, when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes quite spectacularly. So don't take my opinions too seriously. But that's the bottom line as far as I can tell. Now I want to move on to another aspect of vacuum fluctuations, and this is what is called quantum precision measurement technology. And it ties into LIGO and gravitational waves. It was Vladimir Brzezinski, a Russian colleague of mine, who had a huge impact on our LIGO project and on my thinking about physics generally. Again, another Russian who I regard as one of my mentors. Zeldovich and Brzezinski are my two Russian mentors. And he argued in 1968, remember, 68, this is before Weiss had ever invented laser interferometers for gravity wave detection. This is very early. He argued that however you try to detect gravitational waves, you will at some point get to the point where you're trying to measure the motion of large masses at a level that the fluctuations of those masses, centers of mass or whatever it is you're trying to measure, the quantum fluctuations will hide the gravity waves. And he said this is going to be a problem. And then after Ray Weiss invented the gravity wave interferometers, Brzezinski then went in and got a quantitative answer for just where the problem arose. And so he's known where the problem arises from Brzezinski since about 1976. The bottom line is LIGO now is monitoring the motions of 40-kilogram mirrors to a level where the noise is at about a displacement level of 10 to the minus 19 meters, 1/10,000th the nucleus of an atom. And that is beyond the level where quantum fluctuations of the mirror centers of mass start to hide any gravitational wave. And LIGO today is in that range, where we would be dead if we don't have quantum technology to control quantum noise. So let me be more precise about this. But what I'm saying is that for the first time today, we humans see human-sized objects, the centers of masses of LIGO mirrors, behaving quantum mechanically. And that is just a fabulous situation to be in terms of bringing quantum physics up to a human scale. And we have, and people have developed what today is called quantum precision measurement technology to deal with this. Brzezinski's phrase for this was quantum non-demolition measurement technology. You don't want to demolish the gravity wave signal by having these quantum fluctuations or quantum noise get on top of it and hide it. And so you need this technology in order to really succeed when you get to this level. So let me explain what the quantum noises are. There are two quantum noises now in this laser interferometer gravity wave detector. In this gravity wave detector, of course, the gravity wave pulls these masses apart while it's pushing these together, and pushes these apart while it's squeezing these together. And laser interferometry is used to monitor this. And in this scheme, those of you who know about this, and all of you undergraduates, you will learn about this interferometry within the next year or two, probably, if you haven't already. Due to the interferometry, you get a rising and a falling intensity of light going to this photodetector in proportion to the stretch and squeeze of these two arms. Differential stretch and squeeze, a stretch on one arm and a squeeze on the other. And so that's basically what was built in LIGO to search for and monitor passing gravitational waves. Now, the key problem is the fluctuations of the mirror centers of mass, because huge amounts of effort and money have gone into making sure that the centers of mass are what are measured by this interferometry technique. Or more precisely, the distance between those centers of mass minus the distance between these centers of mass. That is the differential change in arm length. So it's a certain combination of centers of mass that's sort of like, let's just say it's this combination of centers of mass, difference between these minus difference between those. And that particular variable fluctuates and due to quantum mechanics. And those are the fluctuations that would be hiding gravitational waves that we are now seeing if we didn't have this new technology. The other quantum noise is one that's more familiar. That's the quantum noise associated with the signal light that is going to the photodetector. The signal light is made up of photons, and the photons arrive randomly. And that random arrival of photons is called shot noise. And that's the second kind of quantum noise. But the quantum noise that I was most concerned about is that of the centers of mass of the mirrors. Carlton Caves, who at the time had just completed his PhD with me, and he was now at that point beginning a postdoctoral position at Caltech. In 1981, he had a brilliant insight that was completely different than what anybody else had ever thought about. People were trying to really understand this more deeply, but he was the first person to think about it in this way. He said vacuum fluctuations of the electromagnetic field entering the interferometer through the output port from the location of the photodetector will go in, and when they split through the beam splitter, they will, when they go up in intensity, in amplitude in this arm, they're going down in amplitude in that arm. And that's just the property of the interferometer. By contrast with the laser light, which goes into the photodetector enters the beam splitter from this side. When it fluctuates up in this arm, it also fluctuates up in that arm. That's pretty obvious with the laser light. Less obvious that the vacuum fluctuations fluctuate up and down, but that's what happens. And he said, look, the vacuum fluctuations fluctuating up in this arm and down in that arm, they will beat against the laser light, which is fluctuating up in both arms and down in both arms, to produce fluctuating light pressure that is antisymmetric between the two arms. So it's beating of light that is symmetric between the two arms with vacuum fluctuations that's antisymmetric between the two arms. And that fluctuating light pressure will in fact control the quantum state of the mirrors. It is the thing that produces the quantum fluctuations of this interferometer's mirrors, produced by the vacuum fluctuations. And similarly, the vacuum fluctuations, having gone into the interferometer and then coming back out, they beat against the outgoing signal light to produce the shot noise. So both the shot noise and the mirror noise, they're both produced by the vacuum fluctuations. And a more precise statement is that the quantum states of the mirror's center of mass and of the signal light are both controlled by the quantum state of the vacuum fluctuations. I mean, it's really quite remarkable. If we've built these interferometers the way that we try to do and make them absolutely immune to everything that we don't want them to be sensitive to, then the only way the external universe can influence these two variables, this quantum state of the outgoing light and the quantum state of the mirrors, is only one way. That is by vacuum fluctuations coming from the output port. And they actually control those quantum states. But if you have then a handle for controlling those quantum states, then you can modify those quantum states in such a way that you can avoid the quantum noise in the gravity wave signal if you're really, really clever. And so it was Carlton Cave said, squeeze them, and I'm not going to explain what squeezing is, but it's something that many of you will know about. It's a technique in quantum optics. Squeeze them in a particular frequency-dependent way so the phase at which you squeeze changes with gravity wave frequency in a particular manner. And with a little help from Bill Unruh, a young colleague at UBC, Caves and Bill Unruh together got this last bit, that if you do this, then you can make the gravity wave signal, you can make the quantum noise go into locations that doesn't affect your gravity wave signal, doesn't affect your measurement. And it is really a beautiful, beautiful theoretical idea. And then it was Jeff Kimball, just down the hall from my group at Caltech, who figured out how to do this squeezing and how to do the rotation of the squeeze phase. And how to do the squeezing in 82, just before he came to Caltech, using degenerate parametric down conversion in a nonlinear crystal, and then how to rotate the squeeze angle by sending the squeezed vacuum through a filter cavity with just the right parameters. And the bottom line is quantum precision measurement technology, which is what we needed. It took 30 years of development by the LIGO team to make this the technology that Jeff Kimball proposed, and he did the early phases of perfecting that technology. It took them 30 years to bring that technology into the LIGO frequency band and to make that technology robust. And it is now operating in LIGO because we need it in LIGO, and it was operating in LIGO when we began to need it because we recognized this was a problem thanks to Brzezinski early on, and we had a total of about 40 years of effort to bring this into being. And it is largely, it is one factor of many, but it is a major factor in LIGO today, seeing several black hole collisions each week compared to one every 6 weeks when it first turned on. And so I just find this a very remarkable development on the side of quantum technology. The future of the warp side research, well, that's in the hands of today's students and postdocs and young faculty. That's you, particularly the undergraduates who will be in the midst of their careers as this really becomes an enormously rich area, while I focus on fun at the interface with the arts. Thank you.
Everyone. So we will take 15 minutes of questions. Max and Dio will run around with the microphones. So raise your hand and I'll call on people.
Is that okay? Hi, hello. Thank you for the talk. It was really enjoyable. Is it working? Okay. I wanted to ask, I think it was 2 years ago, there was a paper published that was a little controversial about how singularities don't physically exist. And there was a lot of back and forth and stuff like that. And I wanted to ask you, in your opinion, the black hole singularity, do you believe that physically exists, and what is it?
So I don't know the paper you're referring to. That is just an indication of the fact that I've been writing poetry. But a singularity is a region where the warping of space and time is embodied, for example, in the Riemann curvature tensor, technically, or in invariance form of the Riemann curvature tensor, like its square, where it diverges, becomes infinitely large formally in general relativity. And we know when it gets very, very large, there are, I think, very solid arguments that say that the laws of quantum gravity will come in and take over. So the issue is whether or not you really ever have, with reasonable initial conditions, do you ever have, generically, do you have singularities form? And as I say, I don't know the paper you're referring to, but there was a lot of work on this, particularly in the 1970s and onward, which I think gave very convincing cases that this does happen inside black holes, and going in the opposite direction that it happened in the Big Bang at the beginning of the universe. But that's what I can tell you. I don't know the recent stuff. If anybody else among the physicists knows it, please speak up. Okay. Okay, any other questions? Okay.
Thank you very much for the talk. I wanted to ask you about closed time-like curves.
Yes.
Are they real? Are they just sort of a mathematical curiosity? Are they of interest?
We don't know for sure. So the kind of question that has been asked, I think answered fairly well, is can the laws of physics adjust in a reasonable way to them if they are allowed to form? And I think there the answer is yes. Of course, the thing you are most concerned about is quantum physics. And so there were two papers around 1990 one by Jim Hartle, the other by John Friedman and colleagues, that both used path integral approaches, so Feynman sum over history approaches, to analyze what would happen if you had a space-time in which you had initially no closed time-like curve, so no possibility of backward time travel. Then you had a localized region that has closed time-like curves, a dischronal region, some people sometimes say, and then that went away. Just assume that's the case. Can you do quantum field theory in the presence of that? And the remarkable thing is that they both came to the same conclusion using rather different techniques, but both based on path integral approach that says, yes, there's no problem. You can compute probabilities for outcomes of experiments, but you lose unitarity. And so the evolution from before the dischronal region to after this dischronal region is non-unitary. Now, I have found this to be very interesting results. And let me say, Jim Hartle was using a variant of path integrals due to Hartle and Gell-Mann. So it was quite interesting. We see Gell-Mann doing all of this stuff using Feynman's ideas. They were friendly competitors at Caltech in my era, in the heyday of physics at Caltech. But the conclusions, as I say, was loss of unitarity. So this makes me suspicious of claims about black hole information loss down black holes. If you have a black hole that forms and then it evaporates by Hawking radiation, is that evolution unitary or not? And the conventional wisdom is that it's unitary because the laws of quantum physics demand it if you use conventional quantum mechanics with the ordinary, usual Hamiltonian type of formulation of quantum mechanics. However, if you use Feynman path integrals, you can deal with more extreme circumstances. And if you use these path integrals, and if there are on a microscopic scale, there are fluctuations in causality. So there are, if you say vacuum fluctuations that include closed time-like curves, that's enough to destroy unitarity in a black hole formation and evaporation. And so my feeling is that in this famous problem, information lost down black holes, which really means non-unitary, or is it unitary or non-unitary for the evolution from before the black hole forms to after it evaporates? My really feeling is we don't know the answer, and the answer is tied up in whether or not the standard formulation of quantum mechanics really is the most fundamental formulation, or is the Feynman approach the most fundamental formulation? The two are equivalent under normal circumstances, but they're not in this kind of a circumstance. So anyway, that's a long comment, but I think a comment that I think is among the most important issues in physics today.
Thank you. Again, thank you for your talk today. Having seen a lifetime of advancement in physics theories, what kind of hopes or like what do you see in the future of theories like string theory or loop quantum gravity?
So through my whole career, I have believed that understanding quantum gravity was the most important problem in physics, and I've completely avoided working on it because my personality, I need some elbow room, and there ain't no elbow room in there. It's a very crowded field with good reason, and so I've chosen to work in areas that at least when I began working on them, that they were not well populated and I had plenty of elbow room. But I've watched from the outside, and I'm impressed by the progress that appears to have been made in both approaches. And I would not be at all surprised if in due course, within a few decades, we come to understand that they are both correct approaches to quantum gravity. Some variant of them both are correct approaches in the same sense as the Schrödinger approach and the Heisenberg approaches to quantum mechanics that looked very different at the beginning turned out to be equivalent. We're not there yet, but I am a strong supporter of the importance of this research and the importance of pursuing not just a string theory or M theory approach, but also pursuing loop quantum gravity and other approaches. And I really do, looking in from the outside, feel that there has been major progress made, but they're not there yet. But again, it's an outsider's view.
Okay, one more question. Over there.
Communicating complex ideas is extremely hard, and you've done that so well. When you were working at Interstellar with other people on the team, did you develop new ideas about wormholes and gravitational waves in the process, or just your past ones?
No, but I did develop a new technology for visualization. So let me just explain. When you're trying to make images, or even more extreme, when you're trying to make movies, videos, where you're trying to visualize things in the vicinity of a black hole, you have to propagate light rays from the source of light through the vicinity of the black hole to a camera. And near the black hole, these tidal forces can take two rays that begin very close together and pry them enormously far apart. So far apart that if you try to interpolate between those rays, you just can't do it. You wind up with jerky or fuzzy images. And this was the experience that the team at Double Negative was having, trying to make images based on the equations that I gave to them for propagation of light in the vicinity of a black hole. So it was actually not me, it was Oliver James at the Double Negative Visual Effects House. They were the people who got the Academy Award for the visual effects in this film. He had the idea, let's propagate a Gaussian beam of light, or Gaussian beams of light, from the source to the camera. And begin with two, in practice you basically propagate from the camera back to the source is the way it's actually done. But begin with overlapping Gaussian beams at the camera, circular cross sections, and propagate them back to the source past the black hole. They'll stretch out, but they'll still be overlapping. And when you get to the source, then you just feed the information from the source into those beams. But by doing it with overlapping Gaussian beams, where you have to propagate not just the central ray, but you have to propagate the size of the beam and its ellipticity, or the two major diameters, and the orientation of the ellipse. So you have to propagate quite a bit more than you usually do. But doing that enabled us to get really good visualizations, just superb visualizations in the film. And so we published in the Journal of Classical and Quantum Gravity the method that we have developed, and then we used it to make images of star fields in the vicinity of a black hole with a camera moving around, and saw some marvelous effects that arise due to caustics in the past light cone of the camera. Things that were known theoretically but had never really been seen. And that paper in Classical Quantum Gravity, I'm told, is by far the most downloaded paper in the history of the journal. Now, how many of those downloaders are physicists and how many are not physicists, I don't know. But this was enormously fun, and it really is was just eye-opening to see the visualizations that we got just from the simple problem of a camera going around the black hole with a spinning black hole with a star field behind it. It's just quite incredible. But that's the only place that I got anything that was really useful for physics. But those techniques are now used by astrophysicists to some degree, and when they're doing visualizations near black holes, and used in Hollywood similarly.
All right, to conclude, I'd like to announce that we're raffling off 3 copies of the book, The Warp Side of Our Universe. You can sign up for the raffle just by registering for our mailing list, which you can find if you just Google Yale SPS Mailman, or by following our Instagram page at Yale SPS. And with that, can we please give one last round of applause for Professor Thorne?
Thank you. Thank you. Let me get my stuff put away before I talk to anybody. After I get my stuff put away. Thank you. Thank you. Let's see,
How do you just go on?
I'm happy to mingle with them for a little while. So I think generally I can do selfies very quickly in photographs. Signing things requires more time, so that if people want photos, let's do that first and see how their time is. Oh, great to see you. Great to see you. So now, who is your father?
My father's Chris.
You're for Chris, yes. Well, give Chris my warm best wishes.
I mean, I'm really glad I got to meet you. I mean, I know that, obviously my grandfather talked a lot about you.
Well, it was wonderful working with him. He was just such a great friend and great physicist.
Yeah. Well, it's great to meet you.
Thank you.
Yeah.
They actually found lots of stuff. Maybe that's what we had.
Like hoisted him up on top of the bus. Yeah, just so much.
Huge. You mentioned the packaging. get like this fun little hexagon. Black computer and black magic. Well, it's the one thing that really touches me about VR.
Coffee chatting.
It does feel quite
I thought you were like a by the talk. Like my legs just said that. I think you guys
I wasn't sure if you
yeah. I didn't like live. Have you looked at I've seen most of it. Yeah. How does it? I like I like how it's beside. I don't know. Yeah. Oh, really? I know, look, it's different. I don't know how your now it's really off. There's like a wall, and then there's like a door. Okay, so one of my friends used to live on the third floor, and his kitchen was open. No wall, no wall. Yeah, it was like a bar. Yeah.
Nicole!
Sorry. Yeah, it looked nice. Oh, like, dang. I'm jealous. Really? Oh, yeah. 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 Okay. Yeah. Like I said, it's where I've always like when I moved here, no one's ever especially with the now. Like all my whole so like, I don't know, it's nice. And I know. I've been. Yeah, smaller. They have like